who attempted that question with a test. So we have a ray of light incidenting on a rectangular prism. We are being told that the refractive index of this is 1.5. So a ray of light incidents on it, this is the normal. You know what, in geometric optics, or what we fervently call as light, because we always measure, there is an incident may be reflected or refracted, there's always the need for the normal. So a ray of light incidents on the prism. And now once this is a glass prism, part of the incident light will be reflected, part of it would also be refracted. But the angle of incidence is always equal to the angle of refraction. So this is the refracted ray. Once this is the angle of incidence, we measure the same value for the angle of refraction as well. So this is also I. Now, if you happen to make this as R, because it's an angle of reflection, yes, it also works out. Then, once this is a glass block or prism, but there will be a refracted ray within the prism. And so this gives us the angle of refraction. Okay, now the question spells out that the angle between the reflected and refracted, this is a refracted. Please give me a minute, I'm coming in. Sorry, I'll be with you. Hello. So this is the reflected ray, this is the refracted ray, and we are told the angle between this is 90. Calculate the angle of incidence. Now, because angle of incidence equals angle of reflection, if this is I, we clear this and then make this I as well. And we are doing this because I is equal to R. This R here is being used for the angle of refraction. So if we apply Snell's law, we have the refractive index equal to sine of I on sine of R. Okay. The refractive index, which is given to us as 1.5, will be equal to sine I over, now what is the value of the angle of refraction? So we are looking for sine R. The angle between the reflected and then the refracted, 90. Okay. Meanwhile, this whole angle must sum up to be 180. So if this is 90, then it means that this angle plus this angle must also sum up to be 90. So that in total we'll have 180. So because I plus R must also be 90 degrees, then out of this, we can find the relation for R, or make R the subject. And we have 90 minus I. So 1.5 is equal to sine of I over sine of 90 minus I. If we use trigonometry to expand this, we've done vectors. So if you use trigonometry to expand this, let's use trigonometry to do this expansion. This will be equal to sine 90 times cos I minus sine I times cos 90. This will be the expansion of this here. Now, when you further expand this, sine 90 is 1. So 1 times cos I is cos of I. Cos 90 is 0. 0 times sine I is 0. So it means that sine 90 minus I is equal to cos I. So straight away, we've expanded this. This is equal to sine I on cos I. And sine of an angle divided by the cosine of the same angle is equal to tan I. So clearly we have tan I is equal to 1.5, which we can easily find. Another way to also simplify this is that draw a right angle triangle of an angle of elevation I. Okay, this is a right angle triangle. So if this is A, B, and C, when you determine sine I from here is equal to A over C. Cos I from here is also equal to B over C. Tan I is equal to A over B. Now, divide sine I by cos I. If you divide sine of I over cos of I, this is equal to A over C divided by B over C. And when you simplify this, this will give us A on C times C on B. This and this will cancel, giving us A over B. That's the ratio of sine I to cos I. Now, because this ratio is equal to A over B, and tan I is also equal to A over B, then we can quickly equate sine I over cos I to tan I. Just to confirm that this ratio is equal to tan I. Or another way out is that we want to understand further, apart from expansion of this, we want to further understand why this sine into bracket 90 minus I is equal to cos I. Another explanation to that is that if this is 90 and this angle is I, what will be this angle? Class, if this is 90 and this is I, what will be this angle? Anybody? Anybody to help? If this is 90 and this is I, what will be this angle? Yes, Michelle. Hello, Michelle. Elizabeth. Please, whoever is ready can answer. If this is 90, this is I, what will be this angle? Oh, please don't waste time in giving me your views. Mamiya, you are also there. Safo and Co. I want a response from you. Hey, Mami, are you there?
Yes, please.
I'm waiting for a response. If this is 90 and this is I, what will be this angle? Do not waste time on this. Hey, what a wow. Elizabeth, go ahead.
Which I think it will also be I.
Come again.
I think it will also be I.
Open your eyes.
It will also be I.
It won't be I. Open your eyes again. If this is,
I said it will also be I.
it won't be I.
Ah.
I. Open your eyes. Mamia.
It means that I and that angle will also add up to 90.
So what will be this angle? That angle.
90 minus I.
Exactly. So Elizabeth, it will be 90 minus I rather, because just as Mamia said, this and this would also add up to 90. So that when we add that to this, we have 180. Are you okay? So this will be 90 minus I. Now, I want you to find cos of I, sine of I. Mamiya, from the right angle triangle, what will be sine of I? Sine of I here. What will be sine I? What will be cos I? Please don't waste time on this. Elizabeth and the rest of you, you are part of the class. Jesse.
Please, sine I is A over C.
Sine I is A on C. Thank you. So A on C. What about cos I? Cos I.
B on C.
So that is B on C. From the same diagram, let's extract sine of 90 minus I. What will be sine of 90 minus I? Nana Safo and Co. Please, if you are ready, let us see what you think. Sine of 90 minus I.
Is B on C.
B on C. Okay, yes. So B on C. And finally, cos of 90 minus I. Cos of 90 minus I. You are wasting time. A on C. Now, when we compare this, we could, if cos I is equal to B on C, and sine 90 minus I is also B and C, B on C, then we can say that sine 90 minus I is equal to cos I. And if cos 90 minus I is equal to A on C, and sine I is also equal to A on C, then we can equate cos 90 minus I to sine I as well. So if we have an expression, 1.5 is equal to sine I over sine of 90 minus I, then we can say that because sine 90 minus I is equal to cos 90 minus I, in place of sine 90 minus I, we can put cos I. So that we have sine I on cos I giving us tan I. And if tan I is equal to 1.5, then I will be equal to the tan inverse of 1.5. A very easy way to determine the refractive, the angle of incidence. So, Maria, what is the tan inverse of 1.5? What's the tan inverse of 1.5? Anybody? Pardon? So we have I to be equal to 56 approximately. So if the angle of incidence, class, if the angle of incidence is 56, what will be the angle of reflection? What will be the value of the angle of reflection? Quick one. If angle of incidence is 56, what will be the angle of reflection? Hey, you are wasting time with your responses or views. Frida.
33.69.
Frida, listen to the question very well. If the angle of incidence is 56, what will be the angle of reflection? Reflection.
56.
Good, 56. And refraction, for refraction, then you subtract 56 from 90. Okay. All right. Let's quickly look at what we're doing under triangular prisms. Please, you are actually delaying in giving your opinion. So look at it again. We don't need to waste time, especially on simple answers. Refraction of light in triangular prism. We went through this. So I'll just touch on whatever or review it a little bit and then we quickly move on. So a triangular prism is this. This is a triangular prism. Its key features are that one, it has this has two refracting planes. Okay. It has two refracting planes. A, B, C. So the two refracting planes are AC and AB. And then it also has a peculiar angle of the prism or refracting angle. So A is the angle of the prism, or refracting angle. So in questions, these are the terms that will be used. Either A, the angle of the prism, A is the angle of the prism or refracting angle of the prism. Now, its advantage is that refraction of light gets deviated when it is incidented. So here for triangular prism, light goes through double refraction before it comes out of the prism or emerges. So it will deviate here, and when it is coming out, it will also deviate here. So light goes through double deviation. Now, its advantage is that this is able to combine refraction at planes AC and refraction at plane AB to give a larger value of deviation. So this, if this is the refracted ray, this gives the total deviation dt. Okay, this is the total deviation, which is the combination of deviation over here and then over here. And because of this special feature, triangular prism is used for the dispersion of light. So it is used for the dispersion of light because light goes through double deviation at both sides of the plane, and then it's able to combine the deviation at both planes, unlike rectangular prism. And so, by using this, we deduce that then the refractive index of the prism can be determined by Snell's law, sine I. This is R1, this is R1, this is R2, R2. So sine I over sine R1. Then we were able to deduce that the angle of the prism A is equal to R1 plus R2. Then we also deduce that the total deviation is equal to D1 plus D2, and we derived D1 to be equal to I minus R1. These are things we went through, the reason for which I'm just touching on them so that we can move on. Then D2 is also equal to the angle of emergence E minus R2. So in substituting D1, D2 into this, we had the total deviation being equal to I minus R1 plus E minus R2. This we rearranged to have I plus E minus R1 plus R2. And because R1 plus R2 is equal to A, we derive an expression for the total deviation to be equal to this. We derive this relation. Then I said that as we increase the deviation, the total deviation, which is this, depends on factors. One of the factors on which the total deviation depends on, we realize is equal to the angle of incidence. Angle of incidence and the angle of the prism. Angle of the prism. The wavelength of the incident light, wavelength of the incident light. And finally, we also realize that the total deviation also depends on the refractive index. Refractive index of the material. Okay, now out of these four conditions, the only one we could control is I, the first one, the angle of the incident, because for angle of the prism, once it's a already made glass, you can't change. Once the glass is already made, you can't change the angle of the prism. The wavelength of the incident light, you can only incident a particular light at a time. And the light, it isn't man-made. You cannot control the wavelength of the light. Then the refractive index. This is made of glass. So long as it is made of glass, I cannot change how this material must bend light. But the only thing I can control is the angle of incidence. okay, is the angle of incidence of the light. And so we saw that as we increase the angle of incidence, the total deviation would also be decreasing, but it would decrease to a certain point, and then from there be increasing. So I remember I gave you a table to complete, and in fact, Frida was the only one who submitted her table, and I'm going to share with you what Frida sent to me. The rest of you did not mind me. Michelle, Elizabeth, Amma, the rest of you, the guys, the gentlemen, no one, responded to my call. Only Frida submitted her table. Let me quickly forward the table to the group. Rather, it will save us that ordeal of recopying. So the table is sent to the group. Please go to the platform to check on the table. I'm going to use it in our discussion, so do so. So we are looking at the last column, dt, the total deviation. So let's compare I to dt, because the argument is that as I increases, total deviation decreases. So we started with when I is 30, 40, 50, 60, 70, 80, and 85. So when I is equal to 30, we have a total deviation of 46.9. When I is equal to 40, we have a total deviation of 38.4. When I is 50, we have 37.2. When I is 60, we have 38.5. When I is 70, we have 42.8. When I is 80, we have 49.2. Then 85, we have 53.3. Now the theory is that as I increases, the total deviation would decrease. So we have the trend being followed: 46.9, 38.4, 37.2. But it would decrease to a particular point, and from there, instead of dt being continuing to decrease, even whilst I is increased, dt will cease to decrease, but rather begin to increase. So we'll get to a point where we have the minimum or the least deviation. And clearly, if we look at what we have, the data we have, this is giving us the minimum deviation. The minimum deviation is 37.2, and at an angle of incidence of 50. Now, at this important point, this important angle, that is where we have the angle of incidence I being equal to the angle of emergence E. So at the minimum deviation, what happens is that we say 1. We deduce that at the minimum deviation, the light ray passes through the glass prism symmetrically. The light or incident, let me add this adjective. The incident ray passes through the prism symmetrically. And 2, angle of incidence is equal to the angle of emergence. 3, we have the first angle of refraction. First angle of refraction Aqua Leonard. First angle of refraction is equal to the second angle of refraction. Angle of refraction. So we are saying that at the minimum deviation, I is equal to E and R1 is equal to R2. For we saw that in refraction of light in rectangular prism, for this refraction of light in a rectangular prism, all the time I is equal to E. So long as these sides are that parallel, I would be equal to E. But it doesn't apply, okay, that is not applied to triangular prisms all the time. It is only on a special situation, and the situation is that it is only at the minimum deviation where the angle of incidence is equal to the angle of emergence. Please take note of that important point. Okay. And so we use this to draw a graph. We plotted a graph of deviation against the angle of incidence. So a graph of dt against I gives us a curve, or yes, a curve like this. Where this point will be equal to that angle of incidence, which gives us the minimum of the minimum deviation. So when we compare it to our values we had, I think the angle of 50 gave us the least deviation. Let me be sure from the table I sent to the group. So the minimum deviation is 37.2, and it occurred at the angle of 50 degrees. So this will be that angle 50. Then 37.2 will be the minimum deviation. And at this particular angle, that is where we have I is equal to E. Then we also have R1 being equal to R2. Okay. Now, if this is what happened, we can use conditions at minimum deviation to find the refractive index of the glass prism. Refractive index of the glass prism before or without minimum deviation, we got that to be sine of I on sine of R1. At the minimum deviation, dt, which is equal to I plus E minus A, this will change to be minimum M. Total will change to minimum because we are at this particular deviation. Will be equal to I, but at the minimum deviation, we have the angle of incidence equal to the angle of emergence. So at the minimum deviation, E is still equal to I. So we have I plus I plus I minus A. This is 2I minus A. And if we make I the subject from what we have here, we have 2I equal to D minimum plus A all divided by 2. So I is equal to D minimum plus A all on 2. Now what will be R? R1. At the minimum deviation, we have R1 is equal to R2. But earlier, we also saw that before minimum deviation, angle of the prism is equal to R1 plus R2. So if at the minimum deviation, R1 is equal to R2, then we only have an angle of refraction. R1 is equal to R2, and they are all equal to R. So if R1 is R and R2 is also R, then we only have 2R. Therefore, R will be equal to A over 2. So we can use conditions at minimum deviation to also find a refractive index, which will be equal to sine of I is this. D minimum plus A all on 2 divided by the sine of R is now this. R is now A over 2. So A on 2. Okay. So this expression, which is, or formula, which is sine dm plus A on 2 over sine A on 2 is the formula that can be used to calculate for the refractive index of the prism at minimum deviation. Okay, and what you have to, or you are expected to obtain, will not be different from the refractive index without minimum deviation. Take note of that. Let's use all that we've done to quickly apply it in problem solving. Let's see how we can use this to solve problems. So I'm going to give you a question, then we see how we can apply all that we've learned to answer. Please, I'm reading, so be attentive. If in a prism, if in a prism, the angle of the prism is 60 degrees, if in a prism, the angle of the prism is 60 degrees, A is equal to 60. And the refractive index is equal to 1.52. The refractive index is equal to 1.52. Calculate the minimum deviation. Calculate the minimum deviation of a ray of light that passes through it. Calculate the minimum deviation of a ray of light that passes through it. And I'm giving you another question. So this is question 1. This is question 1. Question 2. Let me take short of question 2 and then drop it to the group. That will be faster instead. Okay, so I've dropped question 2 on the platform as well. I think the question 1, 2, maybe due to network challenges, some of you could not get it. All right, so I've just dropped question 1, 2 on the platform. I want you to attempt, let's see how you can apply whatever you've learned to solving question 1. So start work. So question 1 is here. Then the first one is question 2. So question 1, if in a prism A is equal to 60 degrees and the refractive index is 1.52, calculate the minimum deviation of a ray of light that passes through it. So try it whilst I take short of attendance, okay? Let's look at it, and then as we go through it, you can, assess whatever you have done. So the first question, if in a prism A is equal to 60 and the refractive index is 1.52, so the angle of the prism A we are told is equal to 60. And then the refractive index is 1.52. Calculate the minimum deviation of a ray. So this question is similar to when I gave you the table to fill. I gave you the value of this. That assume the refractive index of the prism to be 60. And then the angle of the prism, or the refracting angle of the prism, is 60. And the refractive index of the material is 1.5. use a calculation to determine the minimum deviation, and we got that to be 37.2. So we are given a similar question that if the angle of the prism is 60 and the refractive index of the material is 1.52, calculate the minimum deviation of light ray that passes through the prism. So, because n is equal to sine I on sine R, this is without minimum deviation. Now, at minimum deviation, we have this I. I is equal to, don't forget, we derived d minimum is equal to, or we obtained that from dt is equal to I plus E minus A. And then realize that at minimum deviation, this becomes 2I minus A. So at minimum deviation, we have I being equal to dm plus A all on 2. But the question is that we are to find dm. So this will be of no use for now. All that we are looking for is this. So we will need A, we will need I. We have A. How do we determine I? Using n is equal to sine I on sine R, which is also the same as the other formula we derived. Now we have at minimum deviation, R is equal to A on 2. At minimum deviation, R will be equal to A on 2. So if A is 60, then we can easily determine R. R will be 60 on 2, which is 30 degrees. So if R is 30, then 1.52, which is the refractive index of the prism, would be equal to sine I on sine of 30. Sine 30 is half. So sine I will be equal to 1.52 times 0.5. Somebody to help me calculate for I. Help me calculate for the value of I.
Is I is equal to 49.46.
49.46 degrees. Thank you. So if I is this, then the minimum deviation, D minimum, would be equal to 2 times 49.46 minus A. A is 60. So please calculate this for me. 2 times 49.46 minus 60.
Please, you get 38.92.
38.92 degrees. So that will be the minimum deviation of the prism. Okay. Yes, you can. So please, how many of you got this? Raise up your hands for me if you got it right. Refa had it. Who else? David, Anan. More hands. Oh. Okay. There is another way. The other way is using this. Refractive index is equal to sine of minimum deviation plus A over 2 over sine of A on 2. Okay. You will need this. This is given 1.52. A we know, and this is what you are looking for. So you can also use this. But this is, if you understand this, this is easy than, using this blah, blah, blah. Fine, this is also simple though, but so that's it. So please take note, Elizabeth.
See there, please, I used the second method and then I had 40.844.
Let's use it. Let's use it. So if you use the second method, you have 1.52 is equal to sine of dm plus 60 on 2, all divided sorry, all divided by sine of 60 on 2, A on 2. So 1.52 is equal to sine of dm plus 60 on 2 divided by sine of 30. It brings us back to what we were using earlier. Okay, so if you make this the subject, you have sine dm plus 60 all on 2 to be equal to 1.52 times sine 30, which is 0.5. Give me the product of the right-hand side. 1.52 by 0.5.
0.76.
0.76. So we have sine of dm plus 60 all on 2. Now, what I'm looking for is actually what is within the brackets. So let's take the sine inverse of the right-hand side so that we'll be able to handle what is within the bracket. So we have dm plus 60 all on 2 to be equal to sine inverse of 0.76. And what's the sine inverse of 0.76?
49.464.
49.464.
64.
So at this point, I want you to just work it out to make dm the subject. Let me see how you do it. You are calculating for dm, so make dm the subject. Mommy, are you there?
You said that you get the same answer.
Yeah. So I'm sure it's a problem of how you went through making dm the subject. Are you okay?
Yes, please.
All right. The second question. Eva, Nana Safo, once they are not responding, it means they are gone. Mami ya Eva, Nana Safo, they are run away. Oheneba. Those of you who attempted the second question, What answer did you make for question 2? What's your answer before we even solve it?
Please, 48.59.
Who else? Who else was able to finish? Refa, Elizabeth. Okay.
Please, I had 49.673.
We shall see. Let me call on Kelvin and Co. The guys, Leonard, you can't be quiet. William, Safu, you are here. Prince, you are also quiet. Cadmiel, you are all here. Joel, you are all hiding. Frida, you think you are free. Okay, so a ray of light experiences a minimum deviation when passing symmetrically through an equilateral triangular glass prism. Calculate the angle of incidence of the ray. Is that the question? Let me verify if that's exactly what I gave you. Class, is that the question?
Yes, please.
Okay. All right. So now the question is that, you see, we have two different relations at minimum deviation and without minimum deviation. So under which condition or what would the question indicate for us to be sure that, yes, this is a question of at minimum deviation or without minimum deviation? There should be some indicators in the question which would inform you that this is a question of at minimum deviation or not. So you must look at the question carefully. Let's go over the question again. A ray of light experiences minimum deviation when passing symmetrically, okay, through an equilateral triangular prism. So the question has actually made it clear that it experiences minimum deviation. Then I also told you that at minimum deviation, the light ray passes through the prism symmetrically. So all these information are indicators that we are actually talking about conditions of minimum deviation where I is equal to E, R1 is equal to R2. Just that. So these are what must actually be indicated in the question to inform you of how you need to approach the question. Okay, so what is the angle of the prism or the refraction angle of the prism? Prince, can you help us? I want you to tell us the value of the refraction angle of the prism. What is the angle of the prism, Prince? If you have the
please.
Go ahead.
If index or angle.
The angle of the prism or the refracting angle of the prism. What we've been representing by the letter capital A. Okay, maybe
1.5.
Prince, no, we will discuss it. So if you are not clear with that, you understand. The 1.5 is actually the refractive index of the glass prism. Okay, that has been indicated that the refractive index of the prism is 1.5, but the refraction angle, yes, can I get somebody else to help? What is the angle, refraction angle of the prism or the, yes, angle? Frida,
Please, 60 degrees.
why?
Since it's an equilateral triangle, then
So Prince, the question said that it is an equilateral triangular prism. Okay, And we know what an equilateral triangle is. You see, look at this prism. This is an equilateral triangular prism. It means that all the angles 60, 60, 60. So if the prism has equal angles, then it qualifies to be known as equilateral triangular prism. And so the refraction angle or the angle of the prism is 60. Prince, are you okay?
Yes, please.
Okay, so this is 60 degrees. So we are told that the light experiences minimum deviation. Okay, and so we have to calculate the angle of incidence of. So once it experiences minimum deviation, then we know that A will be equal to 2R. We also know that the minimum deviation, D minimum, would be equal to 2I minus A. Okay, and we can also deduce that then the refractive index can be expressed as sine of D minimum plus A all on 2, all divided by sine of A on 2. So we have to calculate for the angle of incidence, right? We have to calculate for the angle of incidence. Okay, so if sine n is equal to sine D minimum plus A all on 2 over sine of A on 2, and we have A, we have N, then we can easily find dm. Here, instead of writing this as dm plus A over 2, I will simply make it I and find I so that I can use this equation to find dm. If you also choose to represent I as dm plus A all on, you are not wrong. Okay. So this sine I is equal to n times sine of A on 2. This is 1.5 times sine of 60 on 2. So 1.5 times sine 30. Sine 30 is 0.5. So when I take the sine inverse of this, I have I to be equal to, yes, what's the sine inverse of this product? Class, what's the sine inverse of this?
48.59 degrees.
48.859.
Yes, please.
Okay, so
Yes,
instead of making it approximately 86. Now, knowing I and dm, oh, I'm asked to find what? I.
Yes, please.
Oh, then we have it. We have I.
rather 48.59,
48.59.
not 48.59.
Now, somebody, you see, I was saying that this is also equal to dm plus A on 2. So instead of I, maybe we want to find dm plus A on 2. Let me rather go through it that way. So we have sine of dm plus a on 2, which is equal to 1.5 times sine of 30. Is equal to 1.5 times 0.5. Therefore, dm plus a on 2 is equal to what you 49.52, right?
59.
dm is equal to 2 times 49.59 minus a. A is 60. So what's the value of dm?
39.18.
39.1 point 39.
8.
Okay. So that because dm is equal to 2i minus a, 2i will be equal to 39.18 plus a, which is 60. Hello?
Please, the sine inverse of the 1.5 times 0.5 is rather 48.59, not 49.59.
48.
0.59.
I'm relying on what you tell me. So please, let's cross check. Okay. So correct dm for me. Correct the value of dm. Correct the value of dm for me.
37.16.
Yes, please.
Okay, 1 8. Sorry.
That's 7.18.
1.8. Yeah.
Okay. So what will be the value of I? What's the value of I?
$48.59.
48.59. So this is the other way out. So either you go by the first method, or you take your time to go through this. Both situations will give you the same story. Now, please, is there any question? If you have any some clarifications to be given, let me know. Do you have any question? Hello? Any question? Then last year, there were some questions in NOVDEC physics under this. In fact, once you have successfully understood this, that would be easy, okay, if it is given to you, which I will. But you see, sometimes you can also, there are some key stuffs you also need to understand under this, especially if you are told that a ray of light incidents on a triangular prism normally or perpendicularly, then you are asked to calculate for the total deviation. Fine, other information can be given to you, but I just want to use this to explain something before giving you. Calculate the value of the total deviation. And the third question, what do they mean? This is a triangular prism. Let's A, B, C. So the refracting planes are actually A, B, and AC. Let's draw a normal to each of these refracting sides. This is N2. So when you incident light here, air to glass, it will be deviated towards the normal. Okay. So this cannot come until the light hits the boundary. So then N2. Then from glass to air bends away from the normal. So when we extend this, let me increase the size of the prism. This is R1. This is R2. So it is under a situation like this that we derived A is equal to R1 plus R2. Then we had the total deviation to be equal to I plus E minus A. Now, if light incidents on the prism normally or perpendicularly, this is what it means. So if this is the normal, N1, then it means that whichever side the light is being incidented from, the light is such that it is along the normal. So it is actually hitting one of the refracting planes at 90. This is what the question means by the light incidenting normally or perpendicularly on the glass prism. And if light incidents on a triangular prism perpendicularly, it means angle of incidence I is equal to 0. I is not equal to 90. Please take note. It's equal to 0 because angle of incidence, angle of reflection, angle of refraction is always measured from the normal. So if the light ray is parallel to the normal or just along the normal, then it means there's no angle between the incident ray and then the normal. So when the light hits on the plane or prism perpendicularly on normally, it means that the angle of incidence is 0. Class, are you okay?
Yes,
Are you okay?
please.
That point, very, very, very important. So you must pay attention. Then, now when light incidents on a triangular prism in this manner, it goes undeviated within the prism. The light, the part of the light that goes undeviated. I want to extend. Friends, are you there?
Yes.
Okay. So when light hits a boundary perpendicularly within the prism, it will go undeviated. So it's similar to under reflection of light in mirrors. When light hits a mirror perpendicularly, it is reflected along the same path. So if this is a mirror and light hits on a mirror at an angle of 90, the incident ray, the reflected ray takes the same path. But for transparent materials, when light hits it at 90, it goes undeviated within the prism. However, when the light is coming out of the prism, then it will bend. The reason why it will bend is that, you see, A, B, C. AC, the light is hitting AC at 90. But AB, is it intersecting AB at 90? Class, is the light intersecting AB at 90?
No, sir.
No. And it is for this reason that the light would bend. Okay. Now, it will bend in such a way that because it is emerging out of glass to air, glass to air, it will bend away from the normal. So within the prism, it is undeviated. But when it is coming out of the prism, then it will deviate. So if the question asks that calculate for the total deviation, this is how to go about it. Because at AC, the light is not bending, it means that R1 is equal to 0. Because if it is bending, look at it. Incident angle of refraction, you have R1. So when you use Snell's law, sine I over sine R1, you can easily calculate for this R1, provided you know I and N. But if it is not bending, then it means under this circumstance, R1 is 0. If R1 is 0, then A, which is equal to R1 plus R2, R2 is just equal to A because this is 0. Class, I hope you are with me. Leslie, are you there?
Yes.
Okay. Now we are calculating for this. Total, we know total deviation to be equal to I plus E minus A. Okay. As for I, because the light is perpendicular to the plane, I is also 0. Angle of incidence is 0, as I said earlier. So I is 0 and R1 will also be 0. But you need the angle of emergence, which is this angle. This is N2. In order to find this deviation, this will be the deviation. Let me extend this line properly. So when I extrapolate the emergence rate, this will be the total deviation, dt, which we are calculating. Okay. So knowing the refractive index of the glass block, you can also use, in fact, if this is dt, then this will be R2. R2. So this is the emergence, angle of emergence E. This is the second angle of refraction. And so when you extend this line, you get the deviation. Okay. So when you manage to determine E, then you can find the total deviation because this is 0. So dt will just be equal to E minus A. A is known. Now the question is that how do we determine E? When you use absolute refractive index. This is when you are assuming that the light is coming from right to left. Then sine E over sine R2. So because A is equal to R1 plus R2 and R1 is 0, it means R2 is equal to A. So you know R2. So you can easily use this to find this information to find E when N is given. Okay, so this is how to go about if you are told that the ray of light incident on the prism perpendicularly. Please, the same thing you can also use reverse refractive index. Meaning if you are going from, absolute refractive index is from air to glass. If you are going from glass to air, then 1 over n, because it's reverse refractive index. Reverse 1 over n will be equal to sine R2 over sine E. And when you make, so these two relations will give you the same answer. Okay, so once you are able to determine E, you can easily substitute it into this relation, subtract A from it, and you have. Please, is there any question? Class, is there any question? All right, au revoir.
Mr. Edia, please, I wanted to ask that in the previous lesson, you said when I is equal to 0, B2 will be equal to E plus A. But then over here, if like we are going by what we just did, we realize that BT is equal to E minus A rather.
Come again. So when in the previous lesson, I said when I is equal to
I is 0, the ray will go through the prism. Yeah, the ray will go through the prism undeflected.
Undeviated.
And then undeviated, sorry. Then D2 will be equal to E plus A.
Is that D2?
Yes.
Small D2.
That's what we saw for the last time. But then today we are seeing that the D total is equal to E minus A. So does it mean that it will be two different things? The D2 then will be different.
I get you, but we are always looking for the total deviation. Okay. So in that case, the D2, as you are saying, would be equal to the total deviation because the ray never got deviated here. So the only deviation we have is when it encounters AB.
Yes.
So in that case, the D2 would actually be equal to DT. DT.
Okay.
So it's basically the same
yes,
thing. But
I get
I am today only looking at it from the total deviation point of view, right? Okay, so let me give you.
Yes, please.
Let me give you an assignment. What you do over the weekend before we meet next week, please. It's a bit tricky question. Whoever gets it will be awarded though. I won't call out the prize. So listen to it. Is that a ray of light passing through a prism having refractive index equal to square root of 2, root 2. Don't panic. Root 2 is just the same as 1.414. So the refractive index given to you in sets is simply the same as when it is given in decimal. So do not panic. So a ray of light passing through a prism having refractive index equal to root of 2 surface minimum deviation. So it is clear to you. Surface minimum deviation. It is found that the angle of incidence is double the angle of refraction. It is found that the angle of incidence is double the angle of refraction. It is found that I is equal to 2 times R. It is found that the angle of incidence is double the angle of refraction within the prism. Within the prism. What is the angle of the prism? Sorry. What is the angle of the prism? So the question requires that you calculate for the angle of the prism. So either angle of the prism or refracting angle of the prism.
Stay there, please. Can you read the question again?
A ray of light passing through a prism, of course, triangular prism, passing through a prism having refractive index of root 2 or equal to root 2. Okay, friends, noted. A ray of light passing through a prism having refractive index root of 2, surface minimum deviation. It is found that the angle of incidence is double the angle of refraction within the prism. The angle of incidence is double the angle of refraction within the prism. What is the angle of prism? Or what is the refraction angle of the prism? Question 2. Another question. Just try for me. Okay. A ray of light undergoes deviation of 30 degrees a ray of light undergoes deviation of 30 degrees when incident on an equilateral triangular prism of refractive index root of 2. So it has the same refractive index as the first one. What is the angle subtended by the ray? What is the angle subtended by the ray within subtended by the ray inside the prism with the base of the prism. What is the angle subtended by the ray inside the prism with the base of the prism? Okay, so do not panic, just give it a try. After that, okay, we'll all discuss it. After all, this is not WASI, so just give it a try. All right. We have about 15 minutes to go, but let's make use of it. I want us to begin with total internal reflection, because TIR and then refraction of light in triangular prism actually goes hand in hand. So total internal reflection. What is total internal reflection? What are the conditions for the occurrence of total internal reflection? Anybody to help? So we are looking at total internal reflection. Also shortened as TIR. What is total internal reflection, and what are the conditions necessary for TIR to occur? Please, can anybody tell us what he or she has learned? William, you have any idea? Michelle, Kelvin, Mamiya, any idea on total internal reflection? Okay. Now, whenever light is incidented, let me see if I can demonstrate this. I wonder if you can see. This is rectangular glass block. I'm incidenting laser. You will not see much. Okay, I think you are seeing an incident and then reflected. Can you see the refracted ray?
Yes, please.
So we have incident, reflected, and then the refracted. The reflected bounces off from the surface. Then the refracted passes through the prism. Okay. Now, whenever light incidents on a surface, and this is a transparent material. This is a normal. We have here the incident light. Part of the incident light will be reflected. So this is the reflected ray, and it obeys the laws of reflection. That angle of incidence equals angle of refraction. Now, part of this incident light will be reflected. So there's the reflected. And then part of it would also be refracted. So this is the refracted. So this becomes the angle of refraction R prime, just to distinguish it from R. So whenever light is incidented on a transparent material, part of the incident light is reflected. part is also refracted. Now, usually you realize that the reflected light would always be weaker. The brightness, okay, will be less. So this will be weaker in terms of brightness, and then the refracted ray is always stronger. And this is because the material is a transparent material. If the material is coated at the back, we have greater percentage of the incident light being reflected. But because this is a transparent material, we have a stronger refracted and then a weaker reflected. And that is what happens whenever light is incidented in a transparent material. Okay. Now, as we vary the angle of incidence, example, maybe I'm choosing angle of incidence of, hello, Erifa.
I wanted to ask that, does this mean total internal reflection in a mirror is different from total internal reflection in the prisms,
Yes,
or they are the same?
they are not the same. There are conditions on which it occurs. So whilst we go through, you understand the condition which would inform the occurrence of this. Okay. Now, as we vary,
Okay, yes.
as we vary the angle of incidence, you realize that whilst we increase I, maybe I starting from 30, 40, 50, 60, you realize that, let me create another diagram to explain it. So we have this, the light is coming from a denser to a less dense. Maybe glass, the dense, let's assume the dense material is glass, the less dense material is air. So the condition is that, the first condition is that for total internal reflection to occur, light must travel from a dense medium to a less dense medium. Okay, so that's the first condition for formation of or occurrence of total internal reflection, from a denser medium to a less dense medium, and not the other way around. That is why I had to clean it to illustrate. So if this is the normal, and then you incident light here, incident, angle of incident I. Now, part of the incident light will be reflected, part would also be refracted. The reflected ray weaker or weak in terms of intensity, and this is stronger. And it's because this is a transparent material. Okay. Still, I is equal to R, or I is I. It obeys the laws of reflection. Now, as we increase the angle of incidence, maybe 30, then we increase it to 40, 50. Now, class, as we increase the angle of incidence, what do you think would happen to the angle of refraction? Will it also increase or decrease? Any view? As we increase the angle of incidence, what do you think will happen to the angle of refraction? Will it increase or decrease? Elizabeth and Co. Frida. Class, I'm asking a question.
Good.
As we increase the angle of incidence, will the angle of refraction increase or decrease? Elizabeth,
Yes, please.
will it increase or decrease as we increase the angle of incidence?
Because I think it will decrease.
Why? Why do you think it will decrease? No reason.
No, please.
Leonard, you are there. Answer. Share your views with us. Leonard, are you there? Oh, Leonard is gone. Okay. It would also increase. The reason is that, you see, the light is from glass to air. And anytime light is moving from denser medium to a less dense medium, it would always deviate away from the normal. So once you increase this, it will further deviate away from the normal because the light is from dense medium to a less dense medium. In this case, from glass to air or water to air. So the angle of refraction would also increase. Elizabeth, are you okay?
Yes, please.
Okay. All right. So you will end here. We'll end here and continue our discussion on total internal reflection next week. I can see you are tired. So we'll continue next week, okay? Continue enjoying your, new year. We will meet once again next week. All right. Please, your assignment. I will indicate the deadline. All right. Until then, in fact, take care of yourselves and bye-bye.
Bye.
Bye.